as well. Here we go. Listening. Shh, shh, shh. Let's recap. Exercise 1A again. 1A, what did we have in exercise 1A? The very first session I taught you, what was it, Naz? Name me one thing you remembered in exercise 1A. Fantastic. Well, those are called set notations. Give me one letter that you know.
Real numbers.
Real numbers. Any number. So we use that. What letter do we use? R. Okay. So normally in your textbooks it's double slash and then R. But I just use R. Okay. So R means real numbers, and we know it's every number that you can think of. So equals any number. Okay. So we're not working with the complex numbers. We're just talking about any number, fractions, decimals, whatever. Yeah. What is Z? Can I please have Daniel? Yeah. What does Z represent? What does it mean? Integers. What is an integer? Can I please have Aiden? Fantastic. Give me an example of a whole number that is positive or negative. 2. 2 is positive. Okay, this is an integer. So -3, that's an integer. Is half an integer? No. Okay, so we've got integers, 2, -3, those are all integers. Whole numbers that are positive, negative. So I'm going to write it here. Whole numbers, positive / neg. Yeah? Does that include 0? Yes, that does. Okay, next one.
Rational numbers.
Rational numbers. What letter would you use for rational numbers, Jerry? Q. Q is your rational numbers. Now, what is a rational number? Can I please have Aunt Sarah? What's a rational number? They're both integers. So when you can write a number where you can express it as a ratio or a fraction of integers. Okay, so if it's A over B, both A and B, where A, B are... So I'm just using their set notation. I'm just saying where A, B is an integer. Okay, so they're a part of the integer system. Okay, so A and B meaning they're both whole numbers or positive or negative. You can express that. So an example would be 3. Why is that a rational number? Because you can write that as 3 on 1. Why is 1/3 a rational number? Because it's an integer and an integer. Both numerator and denominator are whole numbers. Okay, so that's a rational number. And if you convert this to a recurring decimal, it's 0.333 and it carries on. So any repetitive decimals where it has a pattern, it is also a rational number. So if you have rational, you have irrational. Irrational is when you can't do that. Okay? You got R, Z, Q, but let's go to now, what about, and you got N as well for natural numbers. Now what about R plus and R negative? These two, I mentioned that, I said note, and I told you to write that down as your notes. What was R plus again? Can I please have Zan? Okay, that's very good. So you said positive real numbers, not including 0. Now, Sharon, how would you write that using interval notation? So this is a set notation. How do you use it using interval notation? How would you describe it? Positive real numbers, not including 0. So if I want to say R plus, how do I do that with interval notation? Okay, curly bracket 0. This is still set notation. I want interval notation. Interval notation, can I please have Cindy? Open bracket 0. Fantastic. This is an interval because we're going from an interval, yeah, from 0 to infinity, and we're using brackets to denote that. What we're doing here is a set. We're talking about groups. This group, that's a set, and that's an exclusion symbol. Yeah, these are called interval notations. So in exercise 1A, you were learning how to use set notations and interval notations to describe the regions that you have. Yeah. So if R plus is positive real numbers, then obviously R negative would be negative real numbers. Actually, I shouldn't do that. It should be like this: negative, and then same thing, not including 0. Okay. So in that case, your interval notation would be negative infinity to 0. Does that make sense so far? Yeah? Okay, so you had your set notations. We also learned a couple other symbols. We learned this, we learned this, we learned, I'll do that, and actually, Let's go with, who am I chose? Let's go Jack. What's this mean? Intersection. What does intersection mean, Luke?
The elements that are shared between two sets.
Good, fantastic, well spoken. Elements that are shared between two sets. Okay, it basically just means out of two groups, which one is in both, or which one has both in common in both. Okay, what's in common in both? That's what intersection is. What does this symbol mean? What does this symbol mean then? Can I please have, sorry, I forgot your name?
Jason.
Jason.
It's union.
Union. What does union mean though?
Elements that are either set.
In either set. Fantastic. Either is the key word. So elements in either. So you could have this or. Okay, so it means you can have both. Yeah, so it could be chocolate or vanilla. Okay, so you have the choice of chocolate or vanilla. You have both of them. It's not exclusive. Okay? What does this symbol mean then? Can I have this one? What does that mean? Can I please have, let's try to remember some names. That slipped my memory. So what was your name? Rachel? Rachel, what does that symbol mean? An empty set equals empty set. What is an empty set though? There's nothing inside of this group. Okay, so when I say there's nothing inside this group, is that correct?
No.
Why is it incorrect? Because there's a 0 in it. I know I wrote 0, it sounds like it's nothing, but no, 0 is a number. Now I'm saying that in this set, I had the number 0. If you want to say null set, you can either use this symbol, or you can use braces without anything, no elements in there. Okay, so that means there's nothing in this group. And then finally, if I wanted to call this exclusive or excluding, what am I doing wrong? It's a backward slash. Okay, backslash, not forward slash. Backslash or I will.
Backslash.
Thank you. Okay, you said it, I didn't say it. There you go. Backslash. Okay. All right. So those are the symbols that you use, and you're working with your demand and range. That's exercise 1A. Easy. Last week. Yeah. Then we moved on to 1B, and I told you this is the one where I want you to revise, really try to understand it. And we had exercise 1B. What did we work with? Can I please have? What's your name again? Phoebe.
So functions and relations.
Functions and relations. Fantastic. So we had functions and relations. Someone describe to me, what is the definition for a relation? Can I please have, let's go with Heather. Group of coordinates. Fantastic. So a relation is a group of coordinates. It doesn't matter how large or how small the group is, it's just basically a group of coordinates. Okay, now there are 4 types of relations. There are 4 types, I'm going to write here. 4 types of relations. Name me the 4 types. Can I please have, sorry, what was your name again?
Leah.
Leah. 4 types of relations. What are my 4 types? 1 to many. Many to one. Whoops, I'll write it up here. Many to one. Many to many. Great. Now, these are your 4 types of relations. Now, out of those 4 types of relations, 2 of which is a function. Okay, so which one is a function? Can I please have, what was your name? Phoenix. Which one's a function? 1 to 1. Yes, I'm going to do highlight. I'm just going to highlight this. Oh, well, if I can choose it, of course. Oh. Highlight. Okay. 1 to 1 and many to one. What were you looking for? The unique y coordinate. Remember when we say 1 to 1, 1 to many, many to one, many to many, what we're really saying is for every 1x, there is 1 y. For every 1x, there is many y's. And for many x's, there are 1 y. Now remember, a function, the definition was you want one unique y coordinate. Okay, so just to re-jot your memory, we talked about a machine. Okay, well, why is it so hard? We talked about a machine. We said that it didn't matter how many x's you put into this function. Okay, it's only a function is as long as it only spits out one unique y value. Okay, so that's how you know when you look at the relations, you're looking for the second column. If it has a 1 in the second column, that means it is a function. Okay, So that's a function, that's a function, this is a relation, that's a relation. Now, give me an example of a function that is one-to-one. Can I please have, who have I chosen? What's her name again? Is it Shane? Yes, Shane. What's a one-to-one? Like, give me an example of a one-to-one function. Yeah, y equals x. We've got a linear function that looks like this. I'm going to write it here. That's a y, oh, that's not y equals x. Here we go. That's a y equals x. That's a one-to-one. So you can draw, you can see that if you connected the x to the line, there's only one y coordinate connected to that point. Okay, so we draw a point, connected to x, connected to y. That's a one-to-one. Okay, give me another one-to-one function. Can I please have Banu? What's another one-to-one function? Is it Banu?
Yeah.
All right, cool. Yep.
One-to-one.
Yep.
A square root.
A square root function? Yes, a square root function. If you have y equals root of x, if you specifically restrict the domain only, or the range, sorry, from 0 to infinity, yes, we can have a square root function that looks like this. That's a one-to-one. Okay, that's a one-to-one. If you connect the x to this point and you connect it, there's only one y to every one x. Give me another one. Can I please have I chosen everyone? Oh, Lexi. What's another function that's a one-to-one? Ooh. Y equals 1 is a horizontal line that looks like this. So that's at 1. Now, is this a one-to-one? Now, what would this be called? A? No, a. This would be what? We've got, if I chose this x value, I connect to, I got 1 point. So 1x is connected to 1y there. But then if I looked at this x value, I've got now 2. It's also connected to 1. So this is a 2, 1. So 1, 1. So what is this called? Not one to many. Many to 1, because you've got many x's. So remember that many x's to one y value. So this is a function. Yes, you're right. It is a function. It's a linear function. But this is a many x's to one y value. All the y values are the same. Okay? So y equals 1. Okay? Another one for a one-to-one exponential graph. Looks like that. Y equals e to the x. Yeah? That's a one-to-one. You can have a log graph. Y equals log e of x. Okay? That's a one-to-one. All right? So you got your one-to-ones, you got your many-to-ones. Give me another example of a many-to-one. Can I please have Jack?
Quadratic.
Quadratic, yes. Y equals x squared. Y equals cubic, depending on what kind of cubic. Yeah, so if you have x minus 1 squared and x plus 2, yes, you can have a graph like that. That's a cubic, that's a many-to-one. Or quadratic, that's a many-to-one. Okay? What's an example of a one-to-many? What's an example of a one-to-many? Can I please have... Is it Sophie? No, it's not Sophie. What's your name again? Christine. Sorry, Christine. What's an example of one-to-many? So we know it's not a function, it's a relation. Okay, yeah, that's absolutely correct. So this is what we call a square root relation. Okay, so a square root relation where you have the both positive and negative. So remember, one x value is connected to, as you can see, two y values. Okay, so it's one x to many y's. Okay, or you can have a semicircle that's on the side. Okay, really that's a quarter of a circle here, and then a quarter of a circle there if you wanted to sketch that. Okay, but that's a one-to-many. And then an example of many-to-many, the classic one is what shape can I please have? Let's go with Jerry again. Circle, yeah? Circle is an example of a many-to-many. Easy? All right, so that was exercise 1B, and also what I squished in there as well is 1C. Okay, 1C talks about your types of functions and types of relations, sorry, and which ones are functions, which ones are relations. So, what were the key things to look for again? So if I gave you, let's say, 1, 0 with 2, 3, and then, I don't know, let's say 2, 4, and then I give you 5, 6. Is this a function or a relation for this sets of coordinates here? Is this a function or a relation? Can I please have Kate? It's a relation. How did you know? What were you looking for?
Because you've got one x coordinate that's more.
Fantastic. If you have a look for repeated x coordinates, it's a relation. Why? Just think about it on a diagram in your head before you answer the question. 2, 3. So 2 is where x is. 3 is over here. You get a coordinate. But then as soon as you go 2, 4, you can see that x is not only connected to 3, but it's also connected to 4. So that's 1x to many y's. And remember, a function, the definition was, we just said, that it has only one unique y value. So when you don't have a unique y value, you know it's not a function. So repeated x tells you that it is a relation. What happens if you have a repeated y? What does a repeated y tell me? Can I please have, let's go back to Jason.
Repeated y value
Yeah.
would be either a one too many or many too many.
Repeated. Okay, so repeated y values, if you have a set, so let's say you had 2, 3, 4, 3, 5, 6, or 7, 8. Okay, let's say those are my groups. Then the 2, 3, and the 4, 3 could either be, as you said it was,
It's a many to one
it's either a many to one
or many to many.
or a many to many, because it depends on what we're talking about here. But really the 2, 3, if you just picture it, it just means for the y value 3, you have 2 x coordinates. You can have, oh sorry, in our case it was, let's do it over here, 3. It could be 2, so 2, 3, so 2 here, and 4, 3. Okay, you can see that that could end up being a straight line, which is a many to one, many x's. So 2 and 4 is the x-axis, so many x's to one y. Or it could be a circle. See, a circle could be a many to many. Okay, so that horizontal line, that's why we have the horizontal line test and a vertical line test. Because what we're actually doing with the vertical line test is we're just testing, is it a function or is it a relation? Horizontal line test usually tests is it a one-to-one, or is it a many-to-one? Okay, if you know it's a function already. If you don't know if it's a function, then the horizontal line will tell you either it's a many-to-one or a many-to-many. Does that make sense, or have I got a bit too fast there? Cool? All right. So that's exercise 1B and 1C right there. I'm only missing 2 bits, which I taught in the last lesson before I went to camp. What were the 2 bits? So I just talked about all the functions, all the relations, types. What am I missing? What am I missing from 1C? Yes, Naz? Hybrid functions and odd and even functions. Okay, so hybrid functions, like I said, the only thing that you're doing with hybrid functions is just learning to sketch it, and you're just reading the notations, just saying, if this is a function, they give you conditions. You can make up any condition. I can make it up right now. I can do this. I can say maybe from -2 to -1, I want an exponential graph. So I can say that. I can say, I can have e to the x plus 1 from -2 x to -1. I can do that. And then from maybe -1 to 10. So I can say from here, from -1 to 10, I can say I want a quadratic equation where it's x squared. So you can say -1 to 10. Okay, I can do that. Now, just before, when you sketch this, you're simply just breaking it up into its sections. You're finding the endpoints, -2, -1. Where do the endpoints end up? Is it going up? Is it going down? You'll learn to sketch it bits by bit. Okay, so it's a partition or piecewise function is what they call it. And then you can sketch the x squared from -1. So -1 to 10 would be something like, I don't know, x squared, so be closed circle going through, and 10 will give you 100, so it's probably up here. So that's 10, 100. Okay, and then from here onwards, you'll be sketching an e to the x plus 1, which, what's e to the x plus 1? So there'll be an asymptote here. Something like that. I just need to know at -1, e to the -1. Okay, so at this point, it's an open circle, and that's e to the -1 plus 1. Whoops, sorry. What am I doing? -1, e to the -1 plus 1. Have I confused anyone what I just did here? No? So I was trying to find the endpoints, and I know, oh sorry, I haven't figured out this endpoint yet. So -2 would be -2, e -2 plus 1. Okay, I'm just putting in the coordinates for the endpoint. So I know an exponential graph, because it's shifted up by 1, there's an asymptote at 1, so I drew my asymptote, line of asymptote for 1. I've drawn the exponential graph, so this is where it reaches up to -2. I've written down the x and y coordinates at -2. Sub it into the equation, I get e -2 plus 1. Yeah, I'm just subbing -2 in. Same thing with -1 here. I'm just saying -1, when I sub -1 in, where is it on the exponential graph? It's e -1 plus 1. Yeah? Then I drew my quadratic. There you go, that's my hybrid function. Yeah? There's only one thing I want you to pay attention to for your SACs as well, and your exams. When you write out your hybrid functions, notice what I did here deliberately. When I said not equal to -1 here, I put an equals to -1. Now you don't have to have an equals, but if you do have a continuous function, meaning that they all connect, like all the x values are connected, then if you're going to put an equals here, you don't put an equals down here. Because it doesn't make sense if you put equals and equals here, then what happens when x equals -1? Do you sub it in here, or do you sub it in here? Okay, so it has to be clear when you have x equals -1, does it belong to this function, or does it belong to this function? So it matters. So in my case here, I wanted that -1 was not included. That's why at -1, that was not included at that point. But at -1, it belongs to the x squared. That's why I had a closed circle. Does that make sense? Yeah? It's okay.
When there's like purpose at the end, do you label like do you label it on the axis or do you put the point there? Because like I think I remember that you put the point there but didn't reach that point. So you can't mark on if it never reaches that point.
Yep, if it never reaches, oh, so you're saying this one here or you're talking about that one? Both of them. Because of in this particular condition, I specifically said at -2, I want to cut it off there. And at -1, I want to cut off there. That's why you use an open circle. If, for example, if I didn't put a -2 here, and if I said, let's have that as -infinity, then you wouldn't put a point at all. In fact, it would just be, whoops, like that. And it goes on. Is that what you mean, or?
No, like, how can you mark the point of, like, how can you give the coordinates of that point if that point, like, doesn't exist in that graph?
Oh, you mean, those 2 points?
Yeah.
Yeah, absolutely right. But because it doesn't exist, the open circle already means that.
Okay.
But you need to label where the y coordinate, like where would it have been if you did include it. So I'm labeling e to the -1 plus 1. Though it doesn't exist in the function, I still need to know if it were to, what would it be? So that's just sort of being, what do they call it? Being accurate on detail on all your x and y coordinates for endpoints. So these are considered endpoints. Whereas this one that goes to infinity, you don't label that as an endpoint. Okay? Does that all make sense for hybrid functions there? Okay, so there's only tedious because you have to sketch in parts, but see how I do it is I always get the domains correct and then I sketch each graph individually. That's how I do it. Okay? And then lastly, we had odd and even functions. We had odd and even, and there was only 2 things that you had to test. Now, I also did that again in a video for the examples for 1C. I went through a few to show you how I would have done it. Okay, so if you're still confused on this, watch the video again. But what's the mathematical definition to test for an odd? How do you know if it's odd? What do you got to do again? Luke, how do you test again?
I'm entirely sure, but I'm pretty sure that for odd it's, right, for even it's f of x is equal to negative f of x.
Fantastic. Okay, I'm just going to switch that around so it's easy to remember what you need to do. So in order to test, what I'm going to do here, if you want to test if a function is even or odd, there's only one test. The test to see it is what happens if I put a negative number in. That's what this means. It just means in your function, so if I draw a box, all we're saying is what if I put a negative number in there? Okay? Do I get a positive number or do I get a negative number? But this is more specific, not just a number. They want to know, is this number the same as if I just had a positive number in there? Okay, so what we're doing is we're doing 2 tests. We're saying, if I put a positive value, let's say it's equal to 3, right? Then if I put a negative of the same number, so negative value into it, do I still get a 3? Because if I still get a 3, it's likely to be even. Okay, because this is like quadratics. If I put 3 squared, it gives you 9. If I give you negative 3 squared, it still gives you 9. It's the same value. That's why it's even. Yeah? Odd, definition of that is just saying if you put a negative x value in or a negative number in, it gives me the negative of the function. An example would be, so I'll show you two examples here. So this one is x squared, that's an even. So I'll write here even, yeah? You put in -3 and you put in +3, then you get 9. That's even. It's the same thing, yeah? Negative or positive, so negative x or positive x doesn't matter. You get f of 3 regardless. So what I'm saying there is f of -3 is the same thing as f of 3. See how this is exactly the same as what I'm writing up here? Yeah, f of -3 and f of 3, they're both 9. Same thing, so that's even. Odd, on the other hand, basically means that if I put in the number, okay, I put in the number, so let's say, again, -3 and 3, if you think about it, if I put -3, I get -27. If I put 3, I get +27. How do you write that? This is what it's saying. It's saying if you put in f of -3, okay, that's equivalent to the negative of f of 3. That makes sense, because f of, well, I'll just move it across here. See, f of 3 equals 27. You put a negative in front of it, it's -27. It makes sense that -3, if you put it into x cubed, yeah, that's -27. See, this equals -27. This equals negative of f of 3, which is 27. That means the same thing. That's what that mathematical definition is trying to say. Okay? Now, if it doesn't fit in either of those, it's neither. And that's 1C. Easy? Functions, relations, types of relations, implied domains, so you got to read your domain and range. That's from exercise 1A, 1B, okay? And then into 1C, same thing, you still had your hybrid functions, odd and even functions, along with identifying repeated x values or repeated y values. There were the exercises to do there. I did a video on that too, okay? Final one, exercise 1D. Now, if you watch the videos, sums and products. Let's see what you guys learnt. Sums and products. What did I talk? There's only one thing you had to learn from this one. One thing in terms of definition, and then the second part is the skill set. Okay, so what was the one thing? I'll give you a hint. There's an intersection. That's the symbol we use. What was the one definition that you have to make sure in order to even do this exercise? What am I missing? So something intersection. Watch the video, hands up. We've got, let's go with Christine, and then I'll go to you, Jack. Christine, watch the videos. Tell me what you learnt in exercise 1D. What do I talk about? Fantastic. Excellent. Domain of F has to be the same as the domain of G. Okay? The logic here of what I tried to describe in the video, which I'll briefly describe, and that's the only one thing you got to make sure that they'll test. If they talked about sums of function, they asked you to restrict a domain. This is the one thing you have to show that you understood. Sums or products or differences or quotients of functions. Okay? And the only way to add two numbers, subtract two numbers, divide two numbers, or times two numbers is if they're in the same region. You can't add two numbers that are in two separate regions. So, the example I gave in the video was something like this. A square root function, so let's say root of x, and then another one, let's say it was, I think it was a linear graph, but it goes down like this. Okay? What you can see, I'm just gonna give this, I'll make up this one. So let's say negative x minus 1. Okay, so this is minus 1, and that should be minus 1 there too. Okay? What you can see is when you add functions, so if this is, I'll call this f of x, and I'll call this g of x. In this exercise, all you're really trying to understand is two things. One is that definition there. So why does the domain of f have to be, or intersecting, or sort of overlapping with domain of g? It's because of this. When I say f plus g of x, okay, for those who haven't watched the video, this just basically means, what if I took f of x plus g of x? What does that look like? What's that new graph? So what I'm saying is, what if I took negative x minus 1 plus root of x? What if I called that h of x? Sketch that. What does that look like? That's your job. That's what 1D is. To sketch it, there's a set of skills. Watch the video to look at the certain things. But in order to add these to sketch it, there's only one thing you have to check. Domain of f equals to domain of g, or intersects with domain of g. Why is that? See, when you say f of x, this is actually the y values. Remember, this is your y values. That's your y value. Y value, x value. Y value, x value. What they're really saying here is, the sums of these two functions is really saying, take this y value plus this y value. Now what you can see, there's an error already, or there's a problem here. If I talked about x equals -1, if I put -1 into this function here, if I said, let's make it f of -1, f of -1, so I'm saying, what's h of -1? See, the problem here is, f of -1 is fine. The graph of minus x minus 1 has 0 there. See, when x is -1, y 0, I have a y coordinate. It's cool. This equals 0. This ends up being 0. Okay, that's okay. But what's the issue? So if I put a -1 here, so this is -1, and I put a -1 in here, what's root of -1? Undefined. So there's an issue here, because then what is h of -1? Thank you. H of -1 would end up being 0 plus undefined. We don't have an answer. And why does that happen is because the square root function only goes from 0 to infinity. So of course, all the y values are here. This is all your y values, all in the positive region. There is no y values over here. There's no coordinates on this graph, on this square root graph. There is no coordinates over here. That's why the domain has to be both alike. And what's the domain? Right here. So this graph has 0 to infinity. And from here onwards, it's also 0 to infinity. That's why these are the only two y values you can add. Okay? So exercise 1D tests whether you understood this concept. That's the first thing. That you can only multiply two y coordinates if they're in the same region, or you can add the two y coordinates if it's in the same region. Okay? The aim is eventually to sketch that. So your question is, what does this look like? Okay, what does that look like? And there's a few tips on exercise. I'll do a video for 1D. Please watch that. I talk about intercepts, because you know the y coordinate here is 0, plus with -1. Obviously the first coordinate you get is at -1. And you plus all the y coordinates together, and you sort of roughly map what the graph looks like. You'll never be as accurate, but they'll give you graphs such that you can estimate what it should look like. So if you watch the videos, you see how I did it. I did like 3 or 4 examples there, and I showed you how I was thinking about it, and I estimated what it looked like, and I wasn't that far off. Okay? And that's what your skill is meant to do too. So you're meant to be able to sketch sums and products of functions, and you need to understand that that only works when domain of f intersects with domain of g. That summarizes 1A, B, C, D. Cool?
One day in the answers bit, they have some pretty exact graphs. Do we have to
Some of it might be a bit ridiculous.
like
So
some of them I could have get, but some of them were like a bit different.
yeah, then that's fine. If you got most of the main points, like endpoints, maximum minimums, depending on like if they gave you any maximum minimums, any intersections where they start, that's fine. And you get the general gist of the graph, whether it's trending towards up or down. If you get that right, you got most of it right. Really, it's so hard to mark a sums and products of functions. That's why in the exams you don't see many of it. But there has been a few in the last 4 years. So it's worthwhile knowing in case you need to do it. It usually comes up with a sine graph and a cosine graph. The reason why is because it's restricted. You got maximum amplitude, minimum, a minimum maximum, so it's easy to figure out consistently what the space is and how high it goes. That's why they do that, okay? Otherwise, normally you don't get those kind of graphs, okay? So if you have a look at that video, I did 3 examples, and I'm working through the examples with you over that, so please have 1D if you haven't. I know most of you might still be on 1B or 1C, then that's what we're working on, yeah? And that's what this sheet is working on mainly. It's 1B and 1C, okay? Any questions before we revise? And then whatever time left I have, I may talk about composite, or I may leave it to the next session. Okay. Excellent. Grab one, pass it on, please, and then I'll stop the video. Yep. Hopefully, but I spent a bit of time recapping, so maybe not. But we've got a double session, so I reckon we have enough time to have a chat about it. Let's